In this video, we're going to look at the general design process that you want to use when working with controlled systems. So it should be noted that depending on the type of problem you're working with, you might not have to use all of these steps in our process. Particularly for some of our textbook examples that we're going to look at throughout the course, we're not going to be using doing all of these steps in the process. And even in real world applications, for instance, if you're just upgrading or advancing a project that's already been created, you might not need to do some of the earlier steps in this process. So let's go ahead and enumerate each of the 6 steps in this process. Our first step is to transform requirements into a physical system. And so what this is basically just putting our idea into sort of specified words. So we're saying, what do we want to do? How do we want to do it? So we're trying to articulate our general operation, and we're giving some specifications as to how our system needs to operate, what constraints do we have. So articulate general operation, mention any constraints, mention any specifications we have in terms of transient response, in terms of steady state error, things of that nature. So we're just sort of kind of doing a general outline of what we need to do for our problem. Our second step is to draw a functional block diagram. So we want to create a functional block diagram. And so of course in some previous videos we saw some basic examples of block diagrams, and we're going to look at a little more detail in, of course, later units how to create these block diagrams and then how to analyze them as well. So again, we looked at closed and open loop. So depending on what we're designing, we might have one or both of those for various systems. And in addition to this, we might also label what hardware corresponds to certain blocks. Our third step is going to be create a schematic. Clean that up a little bit. So our third step is create a schematic. And so this is a little more free form than our block diagram. So again, whether or not we need to do that and our block diagram is kind of going to depend on the specific problem. But with our schematic, what we want to be doing is we are sort of making assumptions, because we don't necessarily want to include every little effect in there. That's just going to complicate our analysis. But we also want to be checking these assumptions as we go to make sure that we're not getting too far away from what's actually going on in our system. We're not going to focus on the schematics too much. We're going to focus more on block diagrams and a couple other types of representations that we'll get to later on. Our fourth step is going to be to develop a mathematical model. And so this is going to be an important one for us, and this is what we're going to look at in our next unit. So develop a mathematical model for our system. And the way we're going to do this is we're going to use physical laws. So what do I mean by physical laws? So for example, we can use our Kirchhoff's laws. So for our electrical engineers, you should be very familiar with Kirchhoff's voltage law, Kirchhoff's current law, so we're going to be using those. Mechanical engineers, if it's a little fuzzy or if you don't remember that at all, don't worry, we're going to kind of go through what you need to know on that. On the mechanical side, if we're talking about a mechanical system, we can make use of Newton's laws. So we're using these physical laws to develop a mathematical model. How do we do that? We have a few different possible methods. We can use differential equations. We can use something called transfer functions. And with these transfer functions, we're going to be using some type of transform to get into what we're going to call the frequency domain, and we're going to look at Laplace transforms in this class. And then a third one, which we're not going to have time to consider, or most likely not going to have time to consider, is state space analysis. But that is covered in the textbook if you want to go look at that sort of on your own time if we're not able to get to it. The fifth step, which is another one that we don't necessarily always have to do, is to reduce our block diagram. And so if we're looking at our system holistically, so we want to see how our output is related to our input, maybe it's useful to sort of combine all of that stuff in the middle. But if we're just looking at a specific subsystem or a specific block in our diagram, then we don't necessarily need to reduce the block diagram. So again, we can kind of see how we don't necessarily need to do all of these things. Our sixth and final step is very general, is just to analyze and design. And so of course, this is where we're going to spend a lot of our time in later units, is looking at how do we analyze, how do we design. Before we get into our next unit though, the last video in our introduction unit, our next video, is going to cover some specific signals that we use in order to analyze and design signals, just to make sure we're kind of all on the same page in terms of what these signals look like.